And we are live. We're live! Yay! Man, that was difficult. Okay. All right, there we are. There we are. Yes. Okay, good deal. And it's been one thing after another today. Um, as you can see, I look kind of fuzzy. The green screen's not working right. I'm not really certain why. I probably am going to just go ahead and turn it off. I couldn't get the monitor over here to come up to tell me if anybody's talking to me. Um, just bear with me just for a second more, and I'll go into the discussion of uh, this right here. This is what we're going to be talking about. And I'm probably way washed out, but this computer will participate over here. So yes, we're going to be talking about series circuits some more. Imagine that. More series circuit, huh? Yes, it does show me live on YouTube. Okay. Hello, Tim Holmes. How are you? Um, welcome to the channel. Today is, like I said, been a quite a quite a technical disgrace, I guess. But anyway, what I'm doing tonight is I'm going into Module 4, and I guess I better introduce myself. Let me start all over again. Good morning, good afternoon, good evening, no matter where you are around the world. Welcome to Kilroy's World. Welcome to my office. You're welcome, Tim. You're welcome. So what I'm doing, other than messing up the technology, since it's really, like I said, been pretty weird with Streamlabs not working and YouTube not working, I'm going to be talking about series circuits and the voltmeter. And I'll just go through this because we're going to eventually take and make. Let me see if I can grab this without knocking it off. Just bring this over here. So I'm going to be. This is heavy. One of the lessons, one of the labs will be using this DC milliammeter, and what we're going to do is we're going to set it for deflection and turn it into a voltmeter. But anyway, I'm going to go through talking about voltmeters, so I will just begin. The analog voltmeter basically deflects and indicates a number or a deflection, and it's got a little magnetic coil inside that, as current runs through it, it deflects the needle through magnetism. These were used way back, but it really works to simulate how a series circuit application works. And we're going to be talking about the different resistors that you have to put in the circuit so that the current gets limited, so that the needle doesn't go, pegs out totally, and you get full deflection. And of course, that varies on the amount of voltage that you're going to be running through the circuit that you're testing or through the circuit that you're running. And I guess it's going to look pretty bad, I think, but I'm gonna see what it looks like when I go full screen with this. Let me bring this up. It's either that or just totally kill the green screen, and I may just end up killing the green screen. So yeah, that'll work, I guess, for right now. But there's the meter, or a meter, that we're going to be messing with. Like I said, my settings on the green screen got all messed up, but let me lower myself down so I look better. Right. Anyway, I wonder if that helped over there. No, it didn't. So like I said, the analog meter actually reacts to the current that's flowing through there. We're going to use the resistors to limit that current. There's a maximum amount of current that these meters will actually, are actually built for. If you run too much current, can you imagine what happens? I'll let you think about that for a second. So too much current will not only bend, and destroy the needle, but it could cause a fire too, or it could, if nothing else, blow a fuse or melt the thing, or just mess it up, I guess. I'm trying to think where they're used anymore, because they've been replaced by digital displays. Yeah, it cooks. That's right, it cooks. And it cooks and you let the magic smoke out. And when you let the magic smoke out, man, you don't want that. It definitely cooks. So when current flows through the meter, it could give you a voltage drop will occur on the meter, okay? And then that's how the deflection takes place in a sense. And then you can associate where on the meter it is, depending on the current and the voltage drop and the deflection, basically, as to what the actual value is. So meter current and resistance. There's a magnetic coil in there. Yeah, it could well too. That's true. Of course, it probably won't get that bad, but because that's a lot of amperage. We're probably going to be drawing milliamps through here. As you can see, that's milliamps. So it's thousandths of an amp that we're actually pulling through there. But it is designed for a specific it's designed for a specific rating. I mean, like anything, it's got a rating, right? And it's got a resistance in there too. So depending on the resistance, there'll be a voltage drop that drops across there. Then you got to put another resistor in series, like I said, with it, so that the current gets limited running through there. And I know I'm repeating myself, but that's the way it works. If you do it that way, you can use it as a voltmeter, because the actual voltage that drops across here is what the deflection takes, or what the needle displaces is what that deflection becomes. So down here, in this example, and I'm going to go ahead and set this thing down before I drop it or break it. There's a 1 milliamp meter, which is kind of like what we have, and it's got an internal resistance of 3,000 ohms, or 3K. And if we were to measure this, we could actually see what the resistance of this is. Let's see just by chance on this one, but the meter is connected, as the circuit shows, right here, to a 12-volt supply. The resulting current is 4 milliamps that flows through the meter. So if you take voltage divided by resistance is equal to current, you take 12 volts, you divide it by 3,000 ohms, and what you get is 0.004 amps, or 4 milliamps, right? So, but the 4 milliamps is as much, is like 4 times as much as what that particular meter here being displayed is rated at. I don't honestly know what these are rated at. I guess we could look it up with the number, but I am gonna check the resistance on this thing. Set this over to resistance. There we go. I'm gonna set it to 20K. Probably 2,000. No, let's set it to 20K. Turn it on. Let me do something. Let me go big on this. And I'm gonna just move the camera down. So by doing this, you'll see some things here that take place. Let's see if it does it. No, I can see it. Good. I can see it. I can see it. So this right here, I'm going to check the resistance of this meter, and it shows to be 2.4K. What did I put it on? I put it on the 20K range, yeah. And the reason I was kind of looking is because that little cheap meter, the way it looks is I've got 200 ohms there, I've got 2,000 ohms there, and then up here is 20K, but the number's down here, so it kind of looked like the number was right there. That's why I was going, so what's this number? Well, it's that one right there, which is 20K. So what did I say? 2.4? Let me do it again. Let's do it again. Let's do it again. Come on, come on. Yeah, 2.37. Because it's on the 20K range, it's 2.37K. I'm going to write this down somewhere where I can find it again. 2. What did I say? 3.4? 2.7? 2.7? .37 is what I said. And one more time, without my pen in the hand. Yeah, 2.37, 2.36. There. Now we've beat that horse dead, right? Let's go back to this other view. And I guess we can leave that there. It's not really a big deal. So like I said, that meter's got a certain face value of milliamps. And actually, look at this one. You know, I said this one doesn't have, but it does. If you look at the face value of this, let me go back up to the other display. That actually is one milliamp, right? It's if you see it, it starts at 0 and it goes 0.2, 0.4, 0.6, 0.8. So the face value of this is 1 milliamp, just like that up there is. And hey, that says 3K. So really, this meter that we have is pretty much the meter that's being displayed there. Even though that we got 2.37, that's a little low, but close enough. At least we know exactly what we've got on that meter. And I'm really tempted to just go ahead and just kill the green screen. Let me do that. Yeah, I'll have to definitely mess with it. It worked last time pretty well. And I'm thinking I'm just too close to the camera. Let's see, select option. Turn it off. Guess I just gotta take it off. Yeah, let's just take it off. Let's just remove it. Okay, I'll mess with it later. There. That way, all that'll be a big deal is I got a green screen behind me, right? But at least I don't look all washed out and all bad looking, I guess. So, like I said, so if we calculated the current of this meter with the 3K, we come up with about 0.004 amps, which is like 4 times what the actual display is rated at. So what we'd want to do is we would want to take a current limiting resistor and put it in series with the meter. As you can see, here's our meter, and then we're going to take and throw a resistor in the same circuit. And by doing that, not only does it drop voltage here, but it also drops it here. But the main thing is that it takes and it limits the current that's basically flowing through the circuit. Yes, I guess I can raise it up some. And that's why we use current limiting resistors, to limit the current. Duh, right? Yeah, so the value of the resistor can be calculated with, you guessed it, Ohm's law, right? Where's my Ohm's law triangle? Where did it disappear? There it is right there, okay? So, you know, back over here, we said that voltage equals, or current is equal to voltage divided by resistance. If you look at I, and I can't show it. Well, I guess I can. Yeah, right there. If you look at I, I'm actually doing it on the other screen. Yeah. If you look at I right there, and cover it up. That's how I like to put it. Just cover it up. Just put your finger over it. What is the resulting formula? Well, obviously it's, bring this back. Obviously, if you cover it up, then it's voltage divided by resistance, and that's what that's saying right there. So the same thing could be done down here, right? So using Ohm's law, let's go to the next one. We would have to do voltage divided by current, which would be resistance in that case. So if we wanted to know what that resistor, what R2 would be, I guess I probably need to be talking up here. R2 can be found by doing voltage divided by current. Well, what is the current? The current going through here, we really don't know what the current is, but we do know that we only want 1 milliamp of current flowing through here. So automatically we could go over here and put 0.001 as the current, because that's what we want. We want to limit the current in the circuit to 1 milliamp. And by doing that, again, we go back to the formula, which is voltage divided by current, which is equal to resistance. We look at the Ohm's law. We're trying to find a resistor, which is right there. Then a resistance, which is right there. Then it's voltage. Then it's voltage divided by current. So voltage divided by current is 12 volts divided by 0.001 amps. That is equal to 12. That's equal to 12 kilo ohms, or 12 k ohms. So that resistor, if we put that in there with this 3K resistance of the meter, then the actual current flowing through the circuit would be 0.001 amp, 1 milliamp. And that right there would give you what's called full deflection on that meter. It would drive it up. And right now the meter is not adjusted for zero very well, but I guess I could. I think I gotta, maybe I don't. I'm gonna say I probably have a screwdriver that I can, maybe this one will work. Yeah, that might work. I could take and adjust, and maybe not. Let's see if I got a screwdriver right here. But the point being is I can adjust that to be perfectly zeroed, which I'm going to probably end up having to do, so that it's at zero with no current flowing. And then as the voltage goes up, or as we turn it on, we get more current flowing through there. Hello, Ron. How you doing? Um, so that's how we figure out what that resistor needs to be to limit the current through that circuit. So the total resistance of the circuit should be 12K ohms. Now, the series resistor will have a value of 9K, right? Because we figured that it was 12K. So this resistor actually isn't 12K. It's the total resistance in the circuit, which is R1 or R2 plus the resistance of the meter. The two added up is that 12K. So because the internal resistance of the meter is 3K, then we take 12K minus 3K, which is equal to 9K. And then that'll limit the current to 1 milliamp through there, which will mean the meter is fully deflected. So, I'm reading what this says. So we find the current value of the analog meter, right? And this is typically found by just looking at the deflection. And then since that one there is 1 milliamp, or wait a second, it's 100 milliamps, I'm sorry, not 1, then actually if we used the other resistors that we were using, it would only deflect, what, 1/10 of the way up, right? Because it would be 1 milliamp instead of 100, I'm sorry, 100th of the way up instead of all the way over. So the one shown here is 100 milliamps, and it'll cause the meter to, this one shown here is 100 milliamps, 100 milliamps, oh yeah, 100 milliamps will allow it to deflect the whole way. Now, so what we need to do is we need to determine the voltage to be applied to the circuit, right? We need to calculate the total resistance of the circuit when the voltage is measured, and then the current rating of the meter is the things that we need. So we use an ohm meter to measure the resistance of the analog meter, kind of like we did here. Remember, we measured this one and it was 2.37 K ohms, right? I'm going to put down K ohms before I forget. I put the 237, and I always tell students, well, what is it? What's the label on it? You always use the label. And what did I do? I didn't put the label. Shh, don't tell anybody. Okay. So we subtract the resistance of the meter from the total resistance, which we did. Okay, in our case, it was 237 K ohms. And then we place the resistor in series with the meter so that we can make a voltmeter. So we connect the circuit to the meter. The pointer on the analog meter will move to full deflection once it's set up that way. So here's an example. Analog meter is rated at 1 milliamp and 2100 ohms. So determine the series resistor that should be placed in the circuit to measure a 9-volt battery at full scale. Now, that would make this a 9-volt voltmeter, right? And so this example takes us to, okay, we have 9 volts, we have 1 milliamp of deflection, right? So we need a 9K ohm resistance or total resistance in the circuit. And we know we have 2100 ohms in the circuit or in the meter. And we know we need 9K ohms of resistance in the whole circuit. So of course it's that resistor we're going to use there is going to be 9K minus 2100, which in this case it turns out to be 6.9 K ohms or 6900 ohms. So that resistor there, our resistor R3, would be 6900 ohms to make a 1 milliamp meter deflect with 9 volts at full scale. All right, so that's kind of the gist of it. Does anybody have any questions out there? I actually see like 5 people out there. I don't know actually how many officially on. Oh wait. That was weird. Why is that moving like that? I probably know why. Let's see. Bring that up. Pull this over here. something else. I want to see which one I'm. Yeah, okay, we're good. I'm looking over here for a second at my stream. Good, we're still out there, which is good. But I was just double checking YouTube for sure. So let's see. That was the 11.2 info voltmeter. The labs are going to be in here. Just going to go over there, make sure. I think there's 3 labs. And what I'm going to do is look at these other ones. I can't remember. This one's hidden. So let's pull it out of the way. Yeah. Come on. So I've got a worksheet here. Let me go back to. Oh, I was there. Let me look at lab worksheet, which is a PDF, and this is calculating what the multiplier should be on the circuit. I don't think I'm going to assign that one, and that's why I've hidden that one. Series circuits. For some reason, let me go back to module 4. That is module 4. Oh, duh. Press labs. So we're going to be doing series circuit voltmeters, which is lesson 8.1. And in this case, it's pretty much the same thing that we did. We're going to have an analog movement controlled by electromagnets, right? We're going to put a resistor in place. And we'll use the ohm meter to find the resistance of the meter. That's the first step. Then we look at the face of the meter and see what the maximum current is. And I'm pretty certain they're all 0.1, I believe. I think they're all the same. Or I'm sorry, 1 milliamp. I'm pretty certain. There may be some 50 microamp meters in there, but I don't think so. I think I went and looked and found enough of these so that everybody could use the 1 milliamp ones. Then we determine the voltage that we want to measure, and those voltages are down here, 15, 22, 24, and 30. Then we use Ohm's law to determine the resistance of the circuit, which is voltage of the source, which is this voltage, divided by the current of the meter, right? And that gives us a resistance. And then we find the value of the resistor, which is the total resistance minus the resistance of the meter. And that's also in ohms. And then we connect the circuit up, determine the needle of the analog meter to full deflection. If not, you recalculate the problem and you try again. So if you make it wrong, the worst thing is that you use a resistor that's too small and it just pegs it, right? The not so bad thing is if you don't use one that's enough or calculated under, which is probably going to be okay, I guess. And how come it says that I am hosting? See, that's not good. No, yes, maybe. No, that is weird. I'm still live, right? It shows I'm still live. Oh, it must be on the other channel. Okay, it must be over on Twitch. That's what it is. Man, that scared me for a second. I thought I'd gone offline. All right, so back to this. Basically, we just have to find those resistors, kind of like what I showed you a second ago. And you can always, and you will, hook it up to the power supply. Yeah, I am. Yeah, and it is Twitch. I should have looked, Ron, because it's got the little Twitch logo. The chat bot actually chats on Twitch and on or picks up the chat that's going on and the activity, and it must be 9:30. That's when peeper comes on. But it scared me there for a second. So that's one assignment that's going to need to be completed. That's that one, and I went ahead and put it in here just to have it visual. This other one, we're going to kind of use a decade box, which is this little tool right here, which has been used before. And basically, you're going to have somebody else set. It'll be the same. No, actually, we're not going to use a meter. I take that back. But here's what's going to happen. Set the decade box to 1K, right? You read, oh no, this isn't the one. This isn't the one. You set the decade box to 1K. You read the current of the circuit and the voltage drop across the decade box. And that's what this is showing. So you have a meter. And if we don't have enough meters, there are screwdrivers and there are fuses. We're going to be fixing some meters next class, probably. In fact, maybe we'll do this one first, because this one's not too bad. So what we're doing is we're trying to find the unknown resistor values. So we'll set the decade box to 1K. We'll read the current in the circuit and the voltage dropped across the decade box. And then we divide the voltage current by I to calculate the resistance. In other words, voltage divided by current equals resistance. We'll repeat the process using different decade box values. Can you determine the value of the resistance? And I guess I could make this bigger. Can you determine the value of the resistance by knowing its current and voltage? The answer is yes, of course you can. So you position the decade box so you cannot see the values. Yep, you don't want to see the values. Oh yeah, this is the one. And then you have your lab partner take and dial in a resistance. And then using the meter readings, you determine the value of the resistance, the decade box. And then you repeat the process. So you're gonna measure the current, then you're gonna measure the voltage across the decade box, then you're gonna calculate the resistance of the decade box, and then you're gonna have the actual resistance of the decade. So you'll measure the current in the circuit, you'll measure the voltage across the decade box, you'll calculate the resistance because you already know what the measured current is, right? And of course, you know what the voltage is. So then you'll see what the voltage drop is. You calculate that, and then you figure out through Ohm's law, current or resistance is voltage divided by current, right? What the resistance of it is. And as you can see, you've got in the circuit. Oh, we've got an amber alert. All right, so we'll have two resistors, and by the way, it won't matter. Well, I was going to say it won't matter. It will matter because the current will be affected. But if we don't have enough 1K resistors, we'll just substitute two other resistors in there, and then we'll make note of the changes. But the point is we'll have two other resistors in the circuit, and then we'll be changing the decade box for the different resistances. Yeah, Ohm's law is fun, Ron. It is. So that's that assignment, and this one we'll have to practice social distancing, I guess, in some form. Excuse me, but maybe I'll come around. Maybe I'll be the one coming around. How about that? I'll come around, and then your lab partner, because we don't have a lab partner. Yeah, we may change this up a little bit. All right, so that's assignment 2. Assignment 3, we delve into something a little more different, and that is switches. And in this first circuit, we'll have 2 ammeters, or actually we can move from one to the other. Okay, we see what the resistance, what the amperage is here with the meter. We can see what the voltage is. Let me do this again. We can open up the circuit at this point, and let me back up. let me back up. So we have a 10 volt supply, and then a circuit going to a switch, and then that switch is going to a resistor, and then back to the supply. That's the circuit. Okay. So what we'll do first is, with the switch open, we'll take the amperage reading here, and then we'll take the amperage reading here. Did you really, Jeff? Was it an Amarillo one? I don't have it anymore. Oh wait, is it? Oh. No, never mind. I saw it as a Amarillo. But anyway, that's the ammeter 1 reading, the ammeter 2 reading, and then the voltage drops across the switch, and then the voltage drop across the resistor. Then we turn the switch on, and we break the circuit again and put the ammeter in, measure it, and then we measure across the switch. Now, in this case, for this bottom here, the switch is going to be closed. And then we'll check ammeter 2, basically break the circuit right there again and put the ammeter in. And then check the voltmeter, the voltage drop across this resistor. So, remember what we were talking about yesterday? I bet you guys can tell me what the voltage drop is right off the top, with the switch closed, of course. Can anybody tell me? Doom, doom, doom. You don't even need to know what the current is to know what the voltage drop across here. Normally you'd go, the voltage is the current times the resistance. Well, we don't know what the current is. I guess if we put a meter in there, we would, and we would know what the voltage drop is. But because there's nothing else in the circuit, the voltage drop is actually 10 volts across that resistor, because that's really all that's there. So all the voltage gets dropped across the resistor. If we were to put another 1K ohm resistor right here, then the voltage would equally drop 5 volts here and 5 volts here. Let's just say that we put the resistor here where this voltmeter is, okay? With this meter, or with this switch open, we would have a 5 volt voltage drop here and a 5 volt voltage drop here. Now, as soon as we close that switch, in essence, it shorts out that would-be resistor, and then we'd have the total 10 volt drop here. You could have multiple switches in place like this, for instance, and the switches would have to handle whatever current is being drawn. But say this right here was a fan, and this fan had a 1K resistance, which actually probably on that would be a lot, but would get pretty hot. No, I don't know. If we have 1K and we have 10 volts, the amperage, was it for Wales, Texas? See, I saw Amarillo for some reason, Jeff, but I was trying to turn it off, I guess, because of the stream. I probably should have looked at it a little better, but I think you are right. I think it was Wales. So the current in this circuit, knowing that we've got 1K of resistance and 10 volts is voltage divided by resistance, which is what? Is it 0.001? Right? Yeah, it is. I'm pretty certain that my math isn't that bad, but I'm going to go ahead and put it in the old trusty calculator, but it'll come out to 0.001 amps. So we've got voltage, which is 10 volts, divided by 1,000 ohms. Oops. 10 divided by 1,000. And that gives us, ta-da! Did I change it? I don't know if you can see it right there. Let's see. Let's see. 8.1, right there. Whole beans, right? So the current through that resistor would be, and a fan probably wouldn't, 1 milliamp or 0.001 amp wouldn't be enough for a fan, right? But it could be for some form of light. If we had a resistor up here and it was, say, 1K, then the voltage drop splits equally, right? Well, and at that point, when we close this switch, we would get the full voltage drop across here and the current that we just talked about. When we open it, then the path of the circuit changes to, say, if this were a resistor, through here and then through here. And the current would be what? If we add another 1,000 ohms, I'm going to say the current's going to go down by half, because when we would have 10 volts divided by 2,000 ohms, which should be 0.0005, right? Let's just check it just for the sake of continuity, right? So clear that. So 10 volts divided by, where is it? 2,000. And that's 0.005. No, wait a second. Did I? 10 divided by... Oh, by the way, that was 10 milliamps earlier, right? Not 1 milliamp. So it went from 10 milliamps to 5 milliamps. And nobody caught me on that. By adding, say, another resistor up here. And if this were a lamp, for instance, or an LED or whatever device, it would slow down or it would dim. Hello, Rolando. How are you? So that switch could be, made like a dimmer, just an incremental dimmer, some form of control for speed. Now, if you have high loads on it or high currents, then you would actually want resistors that would dissipate the power that's going through there, because the current would be more, and of course the switch would have to handle more too. So all that's got to be taken into consideration. But just in a simple world, you can actually make something to change back and forth. Like, for instance, if you had another switch here where that ammeter is and a resistor, then you could open up both these, and then this other fictitious resistor would be in place, and then the voltage, assuming 1K ohm also, would 1/3 of it would then drop across that resistor, 1/3 would drop across the switch if this were a resistor, and then 1/3 here. So in essence, with both switches open and all three or both resistors and this one, if this were the load, it would be at 1/3 of speed or 1/3 of brightness. If we threw one switch, then it takes one of the resistors out, and then we'd be at 2/3 speed or 2/3 brightness. We threw the other switch, then it would be the back to just one resistor or full power to the so the brighter or the faster it would go, the load would go. Now, well, look, we have multiple switches now, and another little chart to play with. So With this switch here, we're switching between two different paths of the circuit, and this one here the same way. So you can kind of see, though, if you close this switch, this one's closed, then you'll have, you know, your voltage here, and if you open it up, then you're going to get current through here. But the point is, on this one, is that you basically set the switches. Here's switch 1, and here's switch 2. And you set the switch to the A position for switch 1, set the switch for switch 2 to A, and then you read what the voltmeter says, and then you read what the voltmeter says 2, and then you read what the voltmeter says 3. So because these are 3 voltmeters. And you don't have to have 3 voltmeters. You just have to make the connections, or, you know, touch the circuit at those points. And you could in essence leave the meter grounded to the negative side of the power supply, and then as you're going through the changes, you just probe the top of the switch for the A position, for instance, here, and then, you know, probe it wherever it needs to be at whatever point. So you can leave 1 meter lead on the negative side, and maybe an alligator clip is what you're going to use. We'll work those details out, and that, I think, is it for the assignments. Yeah, because that was what I just opened up. Yeah. Now, does anybody have any questions on what I've discussed about the assignments and the lecture? The lecture wasn't that long of a lecture. I went into more of the of the actual assignments. This actually is going to start getting a little more fun, to where we're going to be using meters and making little circuits instead of just hooking up resistors by themselves, right? Let me go back to module 4. Let me make sure there is or there isn't. This is hidden, so I'm not gonna present that one. This is the one that's right there. Okay, that was this one. Oh, there is one more. Yeah, there is one more. I just remembered. Yeah, this one is the one we went over the circuit for meters. Yeah, let me find it here. I know that it's here, and then I'll lecture a little more. That'll be good. This one here. I think it's this one. Oh. No, it's not that one. Nope, it's not that one. Where did I put it? To info. Was it this one? No, this is the lab. This is the lab we just played with. Yeah, no, that's a lab. No, we're not close to parallel yet. That's actually, there's actually going to be a test, believe it or not, Jeff, before we go into parallel. This is kind of rounding it out. There's 3 other videos, and here I'll show them. No, because we're just talking about serial circuits right now. That's why I haven't talked about parallel, but I will be. The streams themselves. Let me go over here. But it is coming. It is coming. So the first stream, Jeff, and I'm not really going to play it, I guess. The first stream was on the ohm meter, and we went into resistor color codes, numbers, and the boards. And look, Ron's even there. Hey, Ron. That was the test stream that we first did. The next one, which was 2 Fridays ago, I think 3 Fridays ago, was and there's the Amber Alert, guys. Was, and I wish there was a little button to go over here. I'm gonna have to put these in playlists because I have to keep going up to videos. Ouch. The next one was Ohm's Law, and that was the DCAC lecture on Ohm's Law, and it was strictly Ohm's Law. And then the last one was series circuits, which is module 3, and then this is series circuits voltmeter. So, yeah. The next, let me look at something here, if I can remember correctly. Yeah. Let me see. Yeah, we're about right here, and we're going to be going into amperage. And see, we're still. No, I take that back. Duh, I take that back. We're right here, in this area right here. The next after the test is going to be parallel circuits, and I'll definitely explain how they how they see. I don't know, the way I do it is I don't explain how they well, they're different, so I explain how they're different, and that's how you get the differences between the series and the parallel. And then we go into series parallel, which is complex circuits, and it starts getting pretty cool down here. We'll start to no, combination circuits. I'm sorry, here. Series parallel circuits, and then eventually we get down to complex circuits and bridges and oscilloscope and such. But we're at this point right here, where we're solving for unknown resistor values using meter readings. So, with that being said, Rolando, do you have any questions? Oh, goodness. You go back. I lost it. Did I close it out? My camera is right in the way, guys. Yeah, I must have closed it out. No, there it is. There it is. Go back to module 4. Does anybody have any questions? Mm-hmm. Okay. Hey, I don't know how long you were here, Rolando. I thought I had seen you earlier too, but I'll go ahead and post the video in the lab, and I'll open up the lab, or I'll open up the module, I should say. So it'll be there. It's I think it's going to be a lot more fun than just putting the resistors together like we have been. But if you don't have any questions, and if nobody has any questions, then I'm going to go ahead and shut the stream down. I think we're at probably about an hour anyway. Yeah. I had a little rocky start. The green screen didn't work the way it should have. But anyway, guys, thank you for showing up. Really appreciate it. If you have any questions, feel free to email me. Feel free to send me something on Facebook. Feel free to put a comment down there. You know the old adage, subscribe, follow, give a thumbs up, definitely put comments down there if you guys have any questions, and I will certainly reply them. So with that, gotta do this backwards. I thought I had put a key combination in, but I guess I'll have to do this the hard way. And the hard way is with the mouse in my left hand, and say, no matter what you do, do it just for fun. Live long and prosper, guys. Have a nice one. Bye-bye.